Welcome back, folks. We're going to get our second fundamental law of circuit analysis. All you MEs out there, you spent a lot of time with that guy named Newton. We've got a set of laws too that help us perform circuit analysis. Everything comes back to these three laws as often as possible, and we're going to get number 2 right now. But we're going to build it off of the voltage divider. Okay, we know how to do some basic voltage dividers. I have one drawn here. Let me bring it up for you. That we already found the values. I think it was the very first voltage divider we looked at in a previous video. But we can see that this 10 volts here comes from the 15 volts across the two things in series, and the 20K was in the numerator, and we got 10K plus 20K in the denominator. Okay, and that's what gave us the 10 volts. Very similar. We got the 5 volts by taking that 15 volts and dividing it across the two, but we're taking the voltage across the 10K in this case, and that gave us the 5 volts. Okay. Well, you may have learned this in your prereqs. We should practice it because we're going to write a lot of these equations. As we begin to analyze circuits, we have to write a lot of these equations. And you may have noticed that, well, 5 plus 10 equals 15, and how does that relate to the circuit, and how do we kind of formally state that in a way that's useful for us in performing circuit analysis? Okay, so here we come with Kirchhoff's voltage law, and very frequently we will abbreviate that as KVL. At least in the English language, that ends up being our abbreviation for Kirchhoff's voltage law. Okay, so if I was going to state Kirchhoff's voltage law, I got it even typed up nicely so you don't have to watch me write it. Okay, so here's his voltage law. So KVL. This is a big one. So big I'll put a box around it. Okay. KVL. The algebraic sum of voltages around a loop in a circuit is 0. So let's unpack that a little bit. Algebraic, if you were going to ignore it, fine, but algebraic, I mean pay attention and respect polarities. Okay, we're going to add everything up, but some of them may be negative values. Okay, and so we have to pay attention to polarity when we're adding energy to the circuit or when we're taking it away. Pay attention to those polarities. The other thing I'll point out is that I use the word loop, and when I introduce loops and they're very closely related, the very closely related concept of meshes, I said I'm going to use these words carefully. I'm saying loop here, and we've got to remember that a mesh is a loop. Okay, but a loop isn't always a mesh. Sometimes it is, not always, but a mesh is always a loop. Okay, maybe I should write the word always in there as well. Okay, so I want to point out those two things as we have that very short sentence that seems simple. Algebraic, we got to pay attention to signs, and it's around a loop, but a mesh is always a loop. Okay, so we have a loop. Hey, look at this loop. It's also a mesh. Okay, in this circuit that we figured out a few videos ago. And what we would like to do, let's name some of these, VS, R1, and R2. What we would like to do is write the KVL equation for this loop. And there's only one loop. There's 3 components. It shouldn't be too bad to begin with. I'll build up in complexity. I want you to be able to do this for some pretty crazy loops and circuits, and ones that you're going to choose ultimately. But we're going to start with a simple circuit, and we're going to build our way up in complexity. Okay, so I'm going to start here, and I'm going to work my way around. So let's grab, we'll go green. Okay, I'm going to work my way around here. remember, for a loop, I have to start and stop at the same place. So if I'm going to write a KVL equation, I have to do the same thing. I have to start and stop at the same place. My habit is to start in the lower left corner. That's my habit. There's nothing preventing me from starting up here or over here, even down there, even though this is all one node along the bottom. So I'm going to start here, and I'm going to work my way around clockwise. Counterclockwise would work just fine also. My habit is clockwise. You can join me in my neuroses of writing these equations habitually, or you can you can go the other way, and that's fine. That's the beauty of some of this stuff, is some of it's up to you. Okay, so if I'm going to start here, every time I move across a component, I have to consider its voltage. Okay, so I'm going to start here, and I'm going to go across it this direction. And as I move from low energy to high energy, I think of that, and again, this is my habit, other people do it differently, I think of that as a voltage rise. So I'm going to call that plus. Okay, you can think of it as, hey, as I move through here, I'm going to pick up the sign as I'm leaving. That's one way I've heard it discussed. But I think of it conceptually, I want to think of it in my head as I am going from low voltage to a higher voltage, and right now I'm going to call that Vs. Okay, so I made that hop. As I move from left to right across R1, I'm moving from high voltage to low voltage. So that's going to be a voltage drop, and I think of that as minus. Okay, and that's going to be VR1. Okay, now I'm over here at this node, and as I move from this node across R2 to this node, I'm going from high voltage to low voltage. So that's going to be another drop. So I'm going to say that's minus, and that's going to be VR2. Okay, now if you leave it like that, it is not an equation. It's not. An equation needs two sides, and I should probably mark points off for that. Sorry, but we're writing a KVL equation, write both sides of the equation. I'm back at this node, which, hey, look, that's the same node I started at, so I've completed my loop. And now that's equal to 0. Okay, and that's what Kirchhoff's voltage law tells us. Now we can plug in values, and you can do this one in your head. They get a little more complicated. We need to work with them symbolically sometimes. 15 was Vs. We have 5 for VR1. Okay, so the sign moves down from the KVL, and then the value gets plugged in. So this sign moves down, and then the value here is 10 volts. Okay, 15, I didn't write my units. 15 volts minus 5 volts minus 10 volts equals 0. Okay, so KVL holds. Even though we found these voltages with the voltage dividers, KVL holds nicely that the sum of the energies needs to be 0 as I move around. Maybe this will help, maybe it'll hurt. Hopefully it helps. Hopefully it does no harm. That's my goal as a teacher. Do no harm. Okay, there's our ground, and as I move from here to here, and every time I move across a component, I'm thinking of taking steps of potential energy, right? So I take that ball and I move it up, and then I let it drop, and then I let it drop again. If it comes back to the same point, all of the energy that I put into it has to come back out of it. Maybe not all at once, but maybe in little steps. Okay, so, right, so the ball goes up one step, and that was a 15 volt rise as I move left to right here, and then we dropped 5 volts. Okay, so this was negative 5 volts, and then we dropped another 10 volts, and we end up back where we started. Okay, so if we put in some energy, it's got to come back out if we get back to the same point. It is conserved after all. All right, the other thing I'll point out quickly is that I have 3 terms. There's 3 components in the loop, right? I've got a voltage supply, a resistor, and a resistor. Okay, so blue. There we go. So there's 3 terms in the KVL. Okay, so the number of terms in the KVL matches the number of elements, components, I kind of use those interchangeably, in the loop. Not in the circuit, but in the loop that we're following. Okay, and it's a KVL, so this one should go without saying, but I'm going to say it so that maybe you get it in your head and you're careful and you check yourself that when you write a KVL, all terms are voltages. Okay, some of you are going to screw that up. I'm sorry to say it, but check to see that all of your terms are voltages. Right now it seems simple when I say that, but as we start writing things symbolically and we start writing KVLs that might involve currents and resistances, currents and impedances, you have to go through and term by term make sure that every term the units work out so that it's ultimately a voltage. Okay, so we need to practice this. We need to write some of these. This one is as simple a KVL as we can get. We need to up the complexity so that you get comfortable writing KVLs as we analyze circuits. Okay, so we're going to do that in the next video. Stay tuned and good luck.